Amazon has just turned on its first humanoid robots. They are not in a test lab. They are walking alongside employees in real warehouses right now. At the same time, a new type of artificial intelligence has just successfully predicted a volcanic eruption 72 hours in advance, an impressive feat that traditional methods have failed to achieve. And in a laboratory miles away, scientists watched in shock as two separate mini-brains, grown on a culture plate, extended neural connections toward each other and began firing in perfect unison. The future isn't just coming. It's being assembled, programmed, and cultivated at this very second. Hello, explorers of the future, and welcome to the channel where we dissect the most impressive news. I am your guide on this journey of the impossible, and what we have this week is not just an update. It is a true redefinition of boundaries. We are witnessing robots that look like they came straight out of a science fiction movie entering the daily workforce, AIs that can sense the fury of nature before it happens, and biotechnology that challenges our very definition of life and consciousness. Today's summary will change your perspective on how fast tomorrow is coming. Let's get started. The industrial automation landscape is about to undergo its biggest transformation in decades. For years, robots in places like factories or distribution centers have been incredibly powerful, but fundamentally limited. Think of the giant robotic arms that assemble cars. They are fixed in place, welding with millimeter precision, but they can't do anything beyond that single task. Or think of warehouse robots, such as Amazon's own Kivas, which glide across the floor. They are efficient, but they are more like glorified shopping carts, following magnetic routes or QR codes on the floor. They exist in a space separate from humans. The big challenge has always been what is called general-purpose automation, a robot that could navigate the human world, deal with the unpredictability of a busy hallway, and perform tasks that weren't perfectly repetitive. That has just changed dramatically. Amazon has officially announced that it is beginning to deploy humanoid digit robots from the company Agility Robotics in its distribution centers in the United States. The videos released are impressive. Digit is a bipedal robot with legs that bend similarly to a bird's, allowing for dynamic balance and two capable arms. It is being tested on a task that, until now, was exclusive to humans: picking up and moving totes, those colorful plastic boxes ubiquitous in warehouses. Robots are seen walking alongside human workers, picking up boxes from one conveyor belt and moving them to another. This is one of the first large-scale commercial uses of humanoids in a real, unpredictable work environment. Here's the simplifying analogy. Today's warehouse robots are like trains, incredibly efficient and strong, but they are stuck on rails or predefined routes. Digit is not a train, it is a passenger. It can walk the same aisles as a human, it can climb a small step if it needs to, it can dodge a cart left in the way, and it can rebalance itself if it gets bumped. It is the fundamental difference between a specialized tool that is bolted to the floor and a true robotic co-worker. Amazon is not adapting its warehouse to the robot. It is deploying a robot that adapts to the warehouse. The future implications of this are profound. Agility Robotics plans to manufacture more than 10,000 digit robots per year at its new factory. We are talking about a new category of workforce. Initially, they will perform repetitive and physically demanding tasks. But Digit is a DBA platform. What happens when its software is updated? When it is integrated with more advanced AI systems, allowing it to learn new tasks just by watching a human? This is not just a new robot. It is the beginning of the era of the general-purpose robotic worker. It's C-3PO's first day at work in the factory. Humanity has always lived under the threat of natural disasters. Among them, Volcanic eruptions are notoriously powerful and terribly difficult to predict accurately. Volcanologists monitor the sleeping giants closely, using a battery of tools. They measure tiny seismic tremors, the volcano's murmur. They use GPS and satellites to detect swelling of the ground as magma rises. And they smell the emissions of gases, such as sulfur dioxide, that escape from fumaroles. The problem is that these signals are often ambiguous. A volcano can grumble for months without erupting, or it can give very subtle signs just before a catastrophic event. Getting the timing right is a game of probabilities with lives at stake. Now, artificial intelligence is offering a powerful new forecasting tool. A new AI model, developed specifically for this task, has just reached an impressive milestone. The system was fed years of seismic archive data, ground deformation data, and gas emission readings from various volcanoes around the world. The AI was trained to find hidden patterns, subtle correlations between thousands of data points that a human analyst could never identify. In a recent test on an active volcano, the details of which are being prepared for publication, the AI model analyzed the data in real time and issued a high probability of eruption alert 72 hours before the event. Most importantly, traditional monitoring methods, while showing some activity, did not provide the same level of certainty or the same lead time. The AI was spot on. The simplifying analogy is this. Traditional methods of predicting volcanoes are like a doctor trying to diagnose a complex patient by only measuring their fever and listening to their cough. They give clues, but not the full picture. The new AI model, on the other hand, is like a super diagnosis. It instantly reads the patient's complete medical history, analyzes all blood tests, gas emissions, listens to the heartbeat, seismic data, checks the MRI, ground swelling, and cross-references all of this with millions of previous medical cases in a matter of seconds. The AI doesn't just see the fever, it sees the underlying cause of the fever and can say with high confidence, this patient will suffer a critical event in exactly 72 hours. The future of this technology is a game-changer for planetary safety. This same type of AI model can be adapted. What about earthquakes? Feed it data on tectonic plate stress. What about tsunamis, predicting their path and impact more accurately? Or even hurricanes, improving the prediction of their intensity? We are essentially building a digital immune system for the planet, a network of sentinel AIs that can warn us about the dangers of nature with a level of advance notice we have never had before. This means more effective evacuations, resource preparation, and, above all, saving countless lives. One of the greatest mysteries in science is the human brain. With its 86 billion neurons, it is the most complex object we know of in the universe. Studying it is incredibly difficult. We cannot simply open up a living person's brain to see how it works in detail. We use scanners, such as fMRI, which show us which areas light up. But this is like looking at a city at night from an airplane. You see the lights, but you don't understand the conversations going on below. To get around this, scientists have created brain organoids. These are mini-brains about the size of a sesame seed, grown in a lab from stem cells. They are not real brains, they have no consciousness, but they develop real types of brain cells and form connections. Recently, scientists at a biotechnology laboratory took this to a whole new and somewhat frightening level. They decided to place two separate brain organoids, but grown from the same stem cells, in the same culture dish. What happened next shocked the team. Within days, the two mini-brains began actively extending neural projections, like tiny electric tentacles, toward each other. They met in the middle of the dish and began to form a bridge, a complex physical neural network connecting the two. But what was most impressive was what the electrodes detected. Once the connection was established, the two organoids began firing in synchronized patterns. They spontaneously formed a unified, functional neural network. The analogy is almost science fiction. Imagine you have two brand new computers in two separate rooms. They are turned on, but they are not connected to the internet and do not have any special software. They are idle. Then a scientist throws a single network cable between the two rooms. The computers weren't programmed to do this, but they detect each other's presence. They start exchanging data packets, negotiating a protocol, and suddenly they start performing the same complex calculation, perfectly synchronized. The brain organoids did this on their own. They self-wired. They detected each other and decided to merge into a larger network. The implications for medicine are revolutionary. We can use these systems to understand how diseases like Alzheimer's or Parkinson's break neural connections. We can test new drugs on real human neural networks without putting a patient at risk. But this also opens up a profound ethical debate. These organoids are becoming more complex. They are beginning to process information. What happens if we connect hundreds of them? What happens if they start to exhibit learning? We are dangerously close to the line that separates biological simulation from the creation of something that may one day feel. It is biopunk territory, reminiscent of Ghost in the Shell, and we are entering it now. In the world of robotics, there is a major dilemma: strength versus delicacy. On the one hand, we have industrial robots that can lift a car with ease, but their claws are crude metal pincers. Try asking one of these robots to pick up an egg or a grape. The result would be a mess. On the other hand, we have tried to create complex robotic hands full of motors and gears, but they are incredibly expensive, difficult to control, and fragile. Nature, however, solved this problem millions of years ago. Just look at the octopus. With its 8 flexible tentacles, it can open a glass jar with brute force and, in the next moment, delicately examine a small shell. Inspired by this master of manipulation, engineers have developed a new soft robotic claw that directly mimics an octopus tentacle. The claw is made entirely of flexible silicone, with no rigid gears or motors. Instead, it uses pneumatics, meaning it is controlled by air channels. By pumping air into or out of different chambers, within the silicone, the claw can bend, twist, and grasp with impressive versatility. Tests have shown that it is strong enough to lift heavy objects, wrapping itself tightly around them. However, in the most impressive test, the same claw was able to approach and pick up a single raspberry without crushing it. A simplifying analogy is to think of traditional robotic grippers as a pair of pliers. They are great for holding a nut or bolt, but terrible for anything else. This new octopus gripper is not a tool. It is a changeable hand. Think of it as a sturdy rubber glove, but filled with a combination of water and sand. When it needs to be strong, the pneumatic system locks the silicone into a rigid shape, like compacted sand. When it needs to be delicate, it relaxes, allowing the air pressure to act like soft muscles, molding itself perfectly around the fragile object, hugging it rather than squeezing it. The future of this technology lies everywhere robots need to interact with the human world, which is fragile and messy. Think of robotic surgery, where a claw like this could manipulate delicate human tissue without causing damage. Think of electronics assembly lines, picking up fragile microchips. Or think of agriculture, with robots capable of picking strawberries or peaches just like a human hand. This is a crucial bridge that allows robots to leave their industrial cages and safely enter our lives, kitchens, and even our bodies. The way we interact with technology has been defined by physical devices. We started with keyboards and mice. Then we evolved to touch screens on our cell phones. Now we are moving to voice with virtual assistants. But all of these interfaces still require us to hold a device or talk to a box. The next step in computing is to make the interface disappear, merging it with us. We've seen attempts with smart glasses and watches, but they're still visible objects that we wear. What if the interface were as subtle as a tattoo? Researchers at MIT have unveiled just that, an e-skin, or electronic skin, that is applied just like a child's temporary tattoo. It is an ultra-thin, flexible sheet that adheres to the skin. But inside this sheet are gold microcircuits, so thin that they move and bend with the epidermis. The most impressive part is its function. These circuits transform an area of the user's skin, such as the forearm, into a functional trackpad. By touching and sliding their fingers over the tattoo on their own arm, users can remotely control their cell phone, computer, or any other connected device. The gold circuits act like the sensors on a laptop trackpad, detecting the position and movement of the finger. To understand this, think of your smartphone's touchscreen. It works by detecting the small electrical charge in your finger when you touch the glass. This MIT tattoo does something similar, but in reverse. Instead of you touching a device, the device is on you. It's as if you temporarily glued the touch-sensitive surface of your favorite trackpad directly onto your arm, but so thin and transparent that it's almost invisible. Gold wires create a sensitive grid on your skin. Sliding your finger over your arm literally becomes the same command as sliding your finger on a mouse. This sounds like something out of Cyberpunk 2077, and that's exactly the way it is. The future implications go far beyond simply changing a song on your phone. Imagine a surgeon controlling a robotic arm with subtle gestures on their own hand, without having to touch an unsterilized screen. Think of astronauts controlling systems in their suits with a simple touch of the arm, or people with motor disabilities gaining a new and discreet way to interact with the digital world. This is true wearable computing, where the line between user and interface begins to blur completely. Ever since we set foot on the moon, the dream has been Mars. But there is one brutal problem: time. With the chemical rocket technology we use today, which is essentially the same controlled explosion technology from the 1960s, a one-way trip to Mars takes 7 to 9 months. It's a long, dangerous, and expensive journey that exposes astronauts to high levels of radiation and muscle atrophy. To truly become an interplanetary species, we don't just need bigger rockets, we need fundamentally different rockets. We need speed. This is where the holy grail of space propulsion comes in: fusion engines. And a space propulsion company has just announced a critical milestone in that quest. They have conducted a successful ignition test, or hot fire, of their new fusion engine prototype. This technology does not burn chemical fuel. Instead, it uses immensely powerful magnetic fields to heat plasma to temperatures of millions of degrees, forcing atoms to fuse, and then ejects that plasma at extreme speeds out the back. The company claims that, once scaled up, this fusion propulsion technology has the potential to reduce travel time to Mars from the current 9 months to an incredible 6 weeks. The simplifying analogy is this: a traditional chemical rocket is like trying to cross the Atlantic Ocean using 1,000,000 fireworks, fired one after the other. You get a huge, brief thrust, then drift along for most of the way, then fire another one. It's terribly inefficient in terms of fuel, for the thrust it generates. A fusion engine, on the other hand, is like creating a small sun contained in the rear of your spacecraft. It doesn't explode, it blows. It generates less but continuous thrust that never stops. It accelerates the ship constantly, day after day, week after week, reaching speeds that chemical rockets could never dream of. It's the difference between trying to move a boat by rowing furiously for 10 seconds and turning on a super-powerful outboard motor that runs for months on end. The future this unlocks is the true space age. If Mars is only 6 weeks away, round trips become practical. We can build bases, send supplies, and rescue crews in emergencies. But it doesn't stop there. Jupiter's moons, such as Europa, with its underground ocean, become reachable destinations. The solar system ceases to be a vast, impassable ocean and becomes a navigable lake. This ignition test is not just about a new engine, it's about lighting the torch that can take us to the stars. What really stands out in this week's summary is the frightening convergence of all these technologies. We saw AI that can predict natural disasters and humanoid robots that can now navigate our workspaces. We've seen robotic claws that mimic the biology of the octopus and electronic skin that fuses our bodies to machines. And meanwhile, we're growing biological neural networks in the lab and building fusion engines to take us to other worlds. The big question that remains is, what happens when Amazon's humanoid robot, Digit, is equipped with the delicacy of an octopus's claw? And what happens when AI that predicts volcanoes is run, not on silicon, but on the biological architecture of brain organoids? We are witnessing not just the advancement of isolated tools, but the birth of an entirely new class of assistants, companions, or perhaps successors. Which of these news stories blew your mind the most? The idea of humanoid robots becoming co-workers, the tattoo skin that turns your arm into a controller, or the 6-week trip to Mars? Leave your opinion here in the comments. If you love staying ahead of the future and understanding the technologies that are shaping our world, don't forget to subscribe to the channel and turn on the bell. The future is stranger and more fascinating than fiction, and we'll cover it every step of the way. See you next time.